Welcome. So, in this lecture, we are going to look at problems and do some calculations from all the concepts that we have learned in the last class. Just to get you started, just to get you started, this is where we are in our course. We are on the last part of our course. Oops, we are in the last part of our course. Fluid reactions. Quick revision of what the things we said in the last lecture. Recall the criteria to be satisfied for different regimes. Write the rate expressions for various regimes. What is meant by enhancement factor? If you revise this, you would be very quickly able to understand what is happening in this lecture. Yeah. Okay. This is just a summary of what we have done in the last class. Okay, let's do a problem. Okay, so calculate regime and rate of reaction of A for the following set of parameters. KL is 10 raised to minus 4, A bar is 100, epsilon L is 0.8, dA and dB both are 10 raised to minus 9 meter square per second, M is 1, N is 1, Z is equal to 1, B naught is 1 kilomole per meter cube, and A star is 0.01 kilomoles per meter cube. What we are going to do is we are going to vary rate constant for the reaction K2 meter cube per kilomole per second, 10 raised to minus 6, 10 raised to minus 4, 10 raised to minus 2, 1, 10 raised to 2, 10 raised to 4, 10 raised to 6, 10 raised to 8. Okay, I want you to complete this table. Pause and complete it yourself. Then you will understand what I am trying to say. Pause. Okay, here is the solution. KLA. So KL is constant, A is constant, A star is constant. Same here. Epsilon L constant, K2 changing, A star constant, B naught constant. So as K2 changes, 10 raised to minus 6, 10 raised to minus 4, 10 raised to minus 2, K epsilon L K2 A star B naught changes. Root M we can calculate, dA constant, K2 changing, B naught constant, KL changing. Root M we can calculate, KL is constant, sorry, so only K2 is changing, right? Calculate. dB B naught by Z dA A star. dB is constant, dA is constant, B naught is constant, A star is constant, Z is constant. Now look at all these things, look at these four things, write the regime, write RA, write enhancement factor. Remember, what is enhancement factor? Rate divided by what would have been in absence of reaction. RA divided by KLA star. Pause. If you have not done this, get up to here, do it for yourself. Then only go forward. This is the answer. Here, look at this. KLA is far greater than epsilon LK2 B naught, like regime 1. KLA is far greater than this, regime 2, regime 1. KLA and epsilon L K2 B epsilon L KL epsilon L K2 A star B naught, they are comparable between 1 and 2. They are comparable between 1 and 2. Root M is greater than 3. Epsilon L K2 A star B naught is greater than, far greater than KLA, regime 3. Regime 4, root M is becoming larger and larger. Reaction is becoming more and more faster. There are diffusion limitations of B. Regime 4. So if you write regime 1, rate expression RA is 8 into 10 raised to minus 9. Regime 1, 8 into 10 raised to minus 7. Regime 2, between these two resistances in series, Regime 3, root M into KLA star. Regime 3, root M into KLA star. Regime 4, KLA star into 1 plus this enhancement factor if you calculate. Obviously, we'll have to calculate from 3 onwards. Rate divided by KLA. So you see enhancement factor is increasing. Regime 3, regime 4. As your rate constant increases, enhancement factor is increasing. Overall rate is increasing. Overall rate is increasing. Very slow, in between very slow and slow, fast, instantaneous. So for a given mass transfer, as I increase the rate constant, more and more enhancement happens, rate of reaction increases. This is like gas absorption. If I do gas absorption physically, it is only by KLA, it is only by mass transfer. As I add a reaction, rate becomes faster and faster. Reactive absorption. So CO2 absorption in water, H2S absorption in water. Rather than that, absorb CO2 in NaOH, absorb CO2 in amines, absorb H2S in amine solutions. Okay. Rate of absorption becomes faster and faster. Enhancement. Right? Very easy to understand. Let's play a trick. Here's another problem. Take A bar is 100, epsilon L is 0.8, dA dB 10 raised to minus 9, same as last time. Take K2 as 1, right? Like this case. M is 1, N is 1, Z is 1, B naught, A star, same as last time. Now vary KL, and complete this table. Pause, do it for yourself. This is what you will get. This is what you will get. Now go forward, identify a regime. Right here, right rate, right enhancement. Tell me what you get. Tell me what you get. Pause, do it for yourself. Pause, do it for yourself. Let's look at first thing. KLA, very less. Epsilon L, K2, A star, B naught, very high. Definitely not regime 1. Would be regime 2, 3, 4. Root M, 3160. Root M is very high. Root M is greater than dB B naught by Z dA star. Regime 4. Right? Regime 4. Look at this case. KLA, epsilon L K2 B naught, comparable. Root M less than 1. This is between 1 and 2. Look at last case. KLA is very high. Rate is very low. Intrinsic epsilon L K2 B naught is very less. Regime 1. So as I increase mass transfer, we go from regime 4 to regime 1. Right, rates. Then you will see. Okay. Here is the answer. Regime 4, 3, 3, 2, 1, 2, 1, 2, 1. Rate. Look at what happens to the rate. Rate is increasing with KL. But what do we call this? We call this an instantaneous reaction. Oops, I should not write it here. We call this as instantaneous. And this as slow, very slow reaction. So very slow and fast and instantaneous. It is with respect to mass transfer. It is not absolute nature of the rate constant. Absolute nature of the rate constant is the same. Absolute value of rate constant is the same. Instantaneous because it is instantaneous as compared to mass transfer. It is very slow as compared to mass transfer. So rate of reaction is highest in regime 1 because if mass transfer is so fast, it is totally not limited by mass transfer. Maximum possible thing that can happen is by intrinsic kinetics. understand that nomenclature of regime 1, 2, 3, 4, very slow, slow, fast, instantaneous, has got nothing to do with the absolute value of rate. It is with respect to mass transfer, what is the phenomena that is happening. Let's go forward. So if you plot enhancement factor with respect to root m, this is what you will get. This is the kind of graph you will get. It will level off if root m is far greater than. So this is the linear portion where e is root m. E is root m. This is the linear portion. And this is the case where e is equal to this value. Right? Oh, this should not be there. Let's pause. Yeah, I made that correction now. Sorry, that term was not there. So root m, e is root m. This is the linear portion. And depending on this value, dB b naught by z dA a star. So if dB b naught by z dA a star is 100, enhancement factor is 100. So you see, this is regime 4. This is like regime 4. Regime 4. This condition is like regime 4. This is how it changes. The straight portion of the graph. This is regime 4. This linear portion is regime 3. And in between, we have between regime 3 and 4. Okay, we are not doing this in between regime 3 and 4. You understand? So if dB b naught by z dA star is 20, let's say, for example. So if root m is more than 20, that's doesn't do the enhancement because you end up in an instantaneous regime 4. So maximum E can be dB b naught by dA. That's why it levels off. And this is between regime 3 and 4. And then finally it is ending in the linear portion here. Root m is greater than 3 up to 20, let's say. So this would be like root m equal to 20. Root m equal to 20. Right? It is stopping here. This is the linear portion. And this is the curved part between 3 and 4. Let's go forward. Let's say H2S is absorbed by an aqueous solution of methanol amine in a packed column. At the top of the column, gas is at 20 atmosphere and it contains 0.1 mole percent H2S, while the absorbent contains 0.25 kilomoles per meter cube of the amine, free amine. Diffusivity is 0.64 times that of H2S, amine. Since it's an acid-base kind of reaction, consider reaction to be irreversible and instantaneous. At the operating condition of the column, KLa is 0.03 per second, Kga is 0.06 kilomole per meter cube per second per atmosphere. Henry's constant for H2S in the liquid is 0.1 meter cube per atmosphere kilomole. Find the rate of absorption of H2S in amine solution. By what factor is the rate of absorption in amine solution higher than that in water? Solve this for yourself. Pause, solve it for yourself. You want hints? Draw a concentration profile and write all the things that we know in the diagram. Pause. Because it is instantaneous, we can say A0 is 0. So if you write H2S profile, this is what happens in the gas. Then it dissolves A star and then it diffuses and reacts. Okay. This is if it is water, no reaction. So Ra would be Kga, Pab minus Pai, Ra would be Kla into A star. And I don't know the interface pressure, therefore I don't know the interface solubility. We can multiply by H, or first expression divide by H if you like. So Ra by H Kga would be Pab by H, Pai minus Pai by H minus Pai by H. And Ra would be Kla and A star. And then these are same. This is just solubility. PAI by H is equal to A star. Henry's law. PAI by H is A star. So Henry's constant. Yeah, I already written there. I don't have to write it again. So RA would be PAB by H 1 by H kGa plus 1 by H 1 by KLA, or if you want you can write it a little bit other way around. RA would be PAB. You can multiply numerator and denominator by H 1 by kGa plus H by KLA. This is how you might have seen in your undergraduate course. Gas side mass transfer resistance and liquid side mass transfer resistance, or gas side mass transfer resistance and liquid side. Now because these are in series, gas side mass transfer and liquid side mass transfer. Substitute the values 0.02, 0.1, substitute and you will get 1 into 10 raised to minus 3 kilomole per meter cube. Resistance in the gas side 166.66, resistance in the liquid side 33.33, which means 83% of the resistance is in the gas side, 16% of the resistance is in the liquid side. Okay, this is like undergraduate stuff, undergraduate material, physical absorption. Okay. Now incorporate reaction, instantaneous, right? Now our situation is lambda and delta. Reaction is instantaneous. B naught is high, then lambda is 0. Right? If lambda is 0, you see this statement we have made, lambda is 0. Why is that? PAB is 2 point, PAB is 20 into 0.1, 0.02 atmosphere. B naught is 0.25 kilomoles per meter cube. B naught by, even if I dissolve, even if there is no gas side mass transfer, what is the maximum value of PAI? Maximum value of PAI would be that in the bulk, 0.02. What is the maximum possible value of A star? That will be 0.02 divided by H. What is H? 0.1. 0.1. This would be 0.2. What is dB B naught by Z dA A star? dB by dA, that is 0.64. Diffusivity of MEA divided by diffusivity of H2S. Z is 1. B naught is 0.25 and this is 0.2. Right? So it is comparable. Right? It is almost 1. It's not that it is very high, but why is that? Why is that? We are in regime 4. We are in regime 4. Okay, it's almost 1. We are in regime 4. If I am saying that there is mass transfer resistance, this is the maximum possible value. Maximum possible value. But PAI is less than 0.02. Correspondingly, A star is less than 0.2. How less? Because gas side resistance is very large. What is it that is going to do? Reaction is instantaneous. It is going to reduce the mass transfer resistance on the liquid side even further. So this resistance is going to be reduced even further, which means it is going to be completely gas side controlled, which means PAI is going to tend to 0, which means A star is going to tend to 0, which means lambda is going to tend to 0, or dB by B naught by Z dA A star, this is going to tend to infinity because A star is tending to 0, therefore lambda is tending to 0, you see, and therefore rate would be kGa into PA, which will be 1.2 into 10 raised to minus 3. enhancement in mass transfer due to chemical reaction is so high that reaction is totally controlled by gas side mass transfer. Resistance has shifted totally to gas side. So rate has increased from 1 into 10 raised to minus 3 to 1.2 into 10 raised to minus 3. Just 20% increase, but because liquid side resistance was already small, already it was only 16%. Already majority of the resistance was gas side. Already it was 83% resistance. Now it is here, it is 100% resistance. So enhancement is only by that factor, 100 by 83.33 or 20% increase. Okay. That's how we are going to solve problems related to mass transfer with chemical reactions. So now you should be able to solve in Levenspiegel's book, chapter 23. You can solve problem number 23.1 to 23.7. And heterogeneous reactions, Doraiswamy Sharma's book, chapter 2. There are some problems at the end of that chapter, but you'll be able to solve them after the next lecture. Okay, this you can definitely solve. Okay? That's the homework. Unless you do this homework, don't go to the next lecture. Okay, we'll stop this lecture here. So we have seen how to use all these and what is the meaning of regime 1, regime 2, regime 3, regime 4. What is the meaning of enhancements? Think about all these things. We have to go to more and more complex problems now. We'll stop this lecture here.